Okay, interference of wave. First, what is it that we want to look at is principle of superposition of wave. So what does it mean by principle of superposition of wave? Principle of superposition states that when two waves overlap that means they go on top of each other. Okay, they go on top of each other. So that is what I mean by overlap. The resultant displacement is the sum of the individual displacement of the two waves. So sum of individual displacement, that means if one wave have a displacement of 1 meter, another wave have displacement of 1 meter also. So when they overlap, the resultant displacement, that means the result is the displacement will become 2 meter. 1 meter overlap with 1 meter, and then the result displacement will become 2 meter. So that is what principle of superposition is talking about. Okay, so we can look at the example for principle of superposition here. For example, we have two waves here. So wave P have amplitude of A, have the amplitude of size A. Q also have amplitude of size A. So during superposition, when they overlap with each other, superposition, the total displacement or the amplitude will become 2A. And then after that, after the superposition, they will continue on with its original direction. That means you look at this, wave Q is going to the left, wave P is going to the right. So this period of superposition, during superposition, this only happen in a very short time. Okay, they move toward each other, and then at the time when they overlap, it will become higher and then continue on. Understand? That means basically it just move pass by each other. The wave P and Q just move pass by each other, but when they overlap, okay, the amplitude temporarily become bigger and then go back to original amplitude, to its own amplitude after that. So this is how we can see the result. After superposition, Q continue left, P continue to the right, and go back to its original displacement of A. The displacement that we are talking about here actually means the amplitude. Okay, understand? The amplitude. If you still remember, I hope you haven't forgot. This is the wave. Okay, this is wave. Amplitude is from here to here. Okay, this is the amplitude. Okay, I hope you still remember. Okay, amplitude. So here it says combined displacement is A plus A, so equals to A. So this is what principle of superposition means. The total displacement is the sum of the two respective displacement. Okay? Alright. So when it becomes bigger, the amplitude, when they superpose, when they overlap and become bigger, we say that at that moment there is interference going on, because they are interfering with each other, right? When they overlap, it causes the amplitude to change, right? So we say that there are interference. You know the meaning of the word interfere or interference, right? In English it means what? Disturb. Very good. 干扰. Okay, interfere. I'm studying. Don't interfere. Jangan kacau. Like that. Okay, interference. So interference occur here. This is where you have interference. This one not yet interference, this one is after the interference. Okay? Understand? Huh? So I hope that you get the idea about interference. Okay, so interference can be divided into two types of interference. We have constructive interference and we have destructive interference. Constructive, like what the word say, you understand what is the meaning of the word constructive, right? Meaning is constructive, 有建设性的 yang membina. Right? For example, can you give me some constructive ideas? Okay, constructive, bagi idea yang cadangan yang membina. Okay, constructive interference membina, 有建设性的. So you see, got constructive, right? The amplitude become bigger, so very obviously constructive. Okay? This one also constructive. When two troughs are in superposition, this is a trough, this is another trough. So when two troughs they superpose and interfere with each other, the resultant displacement also become higher. Negative A, total become negative 2A. So this is also constructive interference. Why? Because the amplitude become bigger. You see that? So it's considered as constructive interference. Same thing after superposition, they go their own way. Continue their own way. Back to original. Okay? Now, that too is constructive interference. Crest, mid-crest. Trough, mid-trough. Constructive interference. Now, how about destructive interference? Like what the name say, destructive, destroy, 破坏, yang memusnah. Okay? It occurs when a crest and a trough are in superposition to produce zero combined displacement. So wave P have the amplitude of A, wave Q have amplitude of negative A. So combine together, A plus negative A equals 0. So you see, during superposition, there is no amplitude. The amplitude is 0. You see or not? No wave. Okay, amplitude 0. After superposition, same thing. They go each their own way. Understand? So one thing that you need to keep in mind, this interference it only occur when they are overlapping each other. That means it only happens for a very short time. If two waves like this, that's all. That is the only moment when you have interference. Okay, okay. So can understand constructive interference and destructive interference. Okay. Pattern of interference for water wave, sound wave, and light wave. Okay. So activity 5.19 to show interference with two coherent sources of wave. Okay, first we want to understand what does it mean by coherent sources of wave. Okay, we want to understand what does it mean by coherent sources. Okay. Okay. Two sources of wave are coherent when the frequency of both waves is the same and the phase difference is constant. So, two wave source or two waves are coherent when both have the same frequency. That is the first thing. Second is phase difference is constant. What does it mean by phase difference is constant? Okay, two waves that have the same frequency does not necessarily mean that the wavelength and the wave speed is the same. Right now, let's say we have two waves. Okay, okay, let's say that split into two, deep two side. Okay, this side is a deep area, this side is shallow. Okay, so when we have wave propagate in the deep region, you see the wavelength is longer. Right? This one shallow, so the wavelength it will be shorter. Even though both have the same frequency, let's say both also come from both come from the same plane dipper. Okay, let's say this is a dipper. Okay, plane dipper. So the plane dipper deep into the water, but one side is deep, one side is shallow. So you can see that the deep part have longer wavelength and the shallow part have shorter wavelength. But both sides, the wave come from the same dipper. If come from the same dipper, that means the frequency must be the same. Both side frequency must be the same. But although same frequency, but the wavelength can be different. The wave speed also can be different. The deep one move faster, the shallow one move slower. So when this happens, one is faster, one is slower, what will happen? The crest and the trough of both waves, they will not be aligned. That means one will be go faster, one go slower like that, for example. Okay, for example, this is crest. So this crest go faster, although both start together. But when this one go to the deep one, this one go shallow, this one become faster, this one slower. You see or not? So this one move forward, this one at the back. One is faster, one is slower. And one side will have longer wavelength, another side will have shorter wavelength. So when this happens, we say that these two waves, are they coherent or not? Not coherent. Because when they one faster, one slower, what happens is the phase difference. Look at here, the phase difference will not be constant. Okay, the phase difference is not constant. If one is faster, one is slower. Understand? What does it mean by phase difference? For example, you have one wave like this, and then, okay, let's say this wave is faster. Sorry, not faster. This wave come out earlier. Okay, this one is produced earlier. Another wave produced later. So like this. This one later. Although one is earlier, one is later. The earlier one, of course, they will be more in front a bit lah. The later that come out one will be at the back a bit. You get the idea? So, although one is earlier, one is later, but both have the same speed. Both have the same wavelength. Both have the same frequency. So when both have the same speed, same wavelength, same frequency, what happens is the phase difference will be the same. For example, when this is crest, this is also crest. When this is trough, this is also trough. And the difference in the phase, this one is faster by, this one is in front, faster by one complete wave, one wavelength, for example, okay, here to here, one wavelength. This one is in front, further ahead by one wavelength. So, even though one is in front, one is at the back, but because they have the same speed, they will, they move like this. So if they move like this, so that means the phase difference is always the same lah. This one, this wave A is always one wavelength in front of wave B. So the phase difference is always the same. Understand? So this is what it means by constant. Phase difference is constant. This is what it means. Okay? Phase difference is constant. This is what it means. Although one is in front, one is at the back, but they move together. So the phase difference is always the same. Understand? Get the idea? So the wave that have same frequency, same phase difference, we say that this kind of wave, they are coherent. Coherent waves. Okay, they are coherent waves. And coherent wave can produce very nice interference pattern. Okay, very nice interference pattern. That is why in experiment that involve interference, we want to use coherent wave. Alright? For example, okay, look at this activity 5.19. To show interference with two coherent sources of wave. A. Pattern of interference for water wave. Apparatus, ripple tank, accessory, and digital xenon stroboscope. Okay, so we use this one. Two spherical dipper. One spherical dipper, two spherical dipper. So the two spherical dipper connect to the same vibrating motor. Okay, connect to the same frequency ripple generator. So if both of them connect to the same ripple generator, that means the wave that they produce must be coherent. Understand? These two dip into the water together. So the wave that is produced is definitely coherent. And the two coherent waves will be able to overlap and produce very nice interference pattern. Okay, so this is how we get coherent wave source in water wave. We connect the two dipper to the same ripple generator. For light wave, how is it that we can get coherent wave? Is we use only one laser pan or only one light source. So the one light source will shine towards a double slit. So the light that go through the double slit will become two coherent wave lah, because for two holes, one go through this hole, one go through this hole, but both of the light come from the same bulb. Understand? Come from the same bulb, So definitely the light that come through here, these two will be coherent. Why coherent? Because both of them come from the same bulb. Understand? Okay, so for pattern of interference for sound wave, same concept. We want coherent source. So what we do is the two speaker we connect to the same audio signal generator. Two speaker connect to the same audio signal generator. So the two speaker will be able to produce sound that are coherent. Boom, 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 both sides together. Okay? Get the idea. Alright. Interference of water wave. We want to look at the result of the activity just now. What will the interference of water wave look like? Figure 5.6 shows the pattern of interference of water wave produced by two coherent sources, S1, S2 in a ripple tank. So this is one dipper, this is another dipper. So these two dipper will dip into the water together, dip, 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 so produce coherent wave. So you see, these two coherent waves, they will overlap each other. Okay, they will overlap each other. So the crest and the crest will produce a bigger crest. Trough and a trough get a bigger trough. This one, crest and trough will get destructive interference, zero amplitude. So that's why you see this point, this point, this point, this point, this point, you see here, 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 here. These are positions where there are destructive interference. Okay, destructive interference. That means the crest meet with trough. That's why you see this area looks like no wave. Okay, look like you see flat. This one bright dark, bright dark, bright dark. That means got wave. Up down, up down, up down, up down. Bright dark, bright dark, bright dark, bright dark. Okay. But this one you see all same color. That means here, over here, all same color. Crest and trough meet together. So become destructive interference, no wave. Here is all constructive interference. Bright dark, bright dark, bright dark, bright dark, constructive interference. This one, destructive interference. Constructive, destructive, constructive, destructive, constructive, destructive, constructive, destructive. Okay. Now, okay, to look at this in more detail, we draw pattern of wave interference. Okay, actually at first I want you to draw, but don't have enough time, so no need to draw. If you want to draw, you can go back and try yourself. Okay, you can go back and try yourself. But what I want you to observe this one. This is very important. Okay, okay, look at here. This one is S1, S2. This is the wave source. The dipper, dip into the water. So this one, the pink color one, this is from source 1. Press, drop, press, drop, press, drop, press. Okay, pink color one. Okay. This one is from the source 1. Press, drop, press, drop, press, drop, press. Yeah, solid line for press, dotted line for drop. Okay. After that, this one source 2 also produce press, drop, press, drop, press, drop, press. And the crest and trough, the wave from source 1, source 2, they will overlap each other. For example, you look at this point. This is what? Trough and trough, right? This one dotted line is trough. This one dotted line also trough. So this is trough and trough. That means we have constructive interference. This point, you see, this is crest, this is trough. This point, crest, trough. So at this point, we will have destructive interference. At this point, destructive interference. So that means here, there will be no wave. The wave will be flat only. No wave. Because destructive interference. So the point where there is destructive interference, these are actually the special point. The point that has destructive interference is the point that is special. Because at first got wave, suddenly become no wave. So it's something special. Okay? Got wave, wave become bigger, not special lah. Got wave, right? But got wave, become no wave. That is special. So the point of destructive interference, we give a name. We call this point of destructive interference as nodes. Nodes. Okay, this point as nodes. And the opposite of node is destructive interference. So constructive interference is the opposite of node, right? So the point of constructive interference we call antinode. Understand? Antinode. A-N-T-I-N-O-D-E. Sorry, my handwriting really bad. Okay. Antinode. Alright. So, you see, along this wave, we will have, for example, here, constructive interference, crest and crest, constructive. Trough and trough, constructive. Crest and crest, constructive. Trough and trough, constructive. So, the line, we can draw a line that connects all the constructive interference. We can draw a line to connect all the antinode. Here, this is all antinode. So we can draw a line, connect all the antinode. So this line that connect all the antinode, we call antinodal line. Okay? And this one is destructive interference. This one is node. This one is node. So the line that connect all the nodes, we call nodal line. Okay? Nodal line. So what is it that we can observe is, you see the pattern. We have antinodal line, nodal line, antinodal line, nodal line, antinodal line, nodal line. Okay? Alternately, the pattern become like that. Okay or not? Okay? You have a pattern that is look like this. So that is why we go back to the this one. You look at this one, You see this one? Bright, dark, bright, dark, bright, dark, bright, dark. So that means this is constructive interference, right? Antinode, 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 antinode. So you can draw a line that connect all the antinode. So this is antinodal line. So this one also antinodal line. This one also antinodal. This one also antinodal line. Antinodal line. Antinodal line. Antinodal line. Antinodal line. Okay, okay, you can see and then in between, we will have, you see this one in between here, don't have bright dark, bright dark, bright dark. So that means we have destructive interference. Destructive interference. So the part where we have destructive interference, that means here we have node. Okay, node. So same thing also, we can draw line to connect all the nodes. So we get nodal line, nodal line, nodal line, nodal line, nodal line, nodal line. Okay, like that. Understand? Okay, now, so you see, that means along the along the antinodal line, the amplitude of the wave will be very high. Okay, the amplitude of the wave is high along the antinodal line. The amplitude is high because constructive interference. So let's say that this is in the sea. Let's say this is in the sea. If you take a boat, motorboat, you ride along the, if you take your motorboat, go along the antinodal line, you will feel your boat, if you take your motorboat along the nodal line, what is it that you feel? No wave lah. Relax, okay? No wave. Okay, you feel no wave. Smooth. Understand? Okay, Okay. Now, what happens if you take your boat, go from here over here? What happens? Okay, understand? Big wave and suddenly small wave. Well, big wave and then small wave, big wave, small wave. Right now. Okay, like that. Okay, now you take a boat, you go along here, right now. You go along here. Okay? You go along here. I put purple color. Okay. Huh? Okay, I use purple color. Here to here. Let's say you take a boat along here, along this line. Okay, you take a boat along this line. From here, go to here. Okay, you take a boat, go over here. So, here to here, okay, the distance from nodal line to nodal line, here to here, here to here, nodal to nodal, nodal to nodal, nodal to nodal line, the distance. This one can see. This one, the distance, nodal to nodal, nodal to nodal, nodal to nodal. Okay, this distance, this is what we call distance between consecutive nodal to nodal line. Okay, this distance we give the symbol of x. Okay, this symbol we give a symbol of x. And the distance will be the same for antinodal to antinodal. From antinodal line to antinodal line, the distance we also label as x. Okay, so this is, we label this as x. Okay, so this x is distance between consecutive nodal to nodal, antinodal to antinodal line. Okay, this is x. And then the distance between the two coherent wave source. The distance between the two coherent wave source, we give the symbol A, the small a. And then the distance, the perpendicular distance from the point of measuring the x to the coherent wave source. That means this distance here to here, this is 90 degree, 90 degree, 90 degree. That is why we say perpendicular distance from the coherent wave source to the position where we measure x. This distance we give the symbol D, a capital D. So we have three variables here, A, X, and D. A is the distance between coherent wave source. X is consecutive distance between consecutive nodal to nodal, antinodal to antinodal line. And D is the distance from, D is the perpendicular distance from coherent wave source to position of measuring x. We have A, we have X, we have D. And from experiment, that means we do experiment by manipulating the A, manipulating the D, we find the relationship between A, X, and D, and then we find that we can calculate the wavelength with the relationship between A, X, and D. So we find like this. The result is we find that the wavelength will be equal to A times X over D. Okay, this is the result of the relationship between A, X, and D. Okay, we find that A times X divided by D, we can get the wavelength. Okay? We find that A times X divided by D, we can get wavelength of the wave. Now, this is a very important discovery. This equation is a very important discovery. Why is it very important? Because wavelength of water wave, you can see with your eyes, right or not? Ripple tank, you can see, you can measure. But how about wavelength of sound wave? Can you see the wavelength of sound wave? Cannot see, right? Oh, measure. Cannot, right? How about the wavelength of light? See the light. Measure the wavelength. Can you see the wavelength of the light or not? Measure the wavelength of the light. Okay? Cannot measure, right? Cannot measure. Okay? So, that means what? Is it impossible to get the wavelength of sound and the wavelength of light? Is it impossible? Yes, we can get the. It's not impossible. Why? Because of this equation. Wavelength equal AX over D. That is why this equation is so important. It let us calculate, let us find out the wavelength of sound, the wavelength of light wave. Get the idea? But first, of course, we need to get interference of sound, interference of light, so that we can take the A of the light. Okay, when we do experiment for light, we take the A, X, and D for the experiment of the light interference. Then we can calculate the wavelength of light. We get the A, X, and D for the interference experiment for sound. Then we can calculate the wavelength of sound. You see or not? And when we get the wavelength, we are one step closer to calculating what? Calculating their speed. Right? If you know for sound, you can get the frequency, you can get the wavelength, then we can calculate the speed of sound. Get the idea? For light, if we can calculate the speed of light, we can get the speed of light, we can get the wavelength, we can calculate the frequency of the light. Okay? So that means slowly we get this information a bit from another experiment. We get this information, we combine together, we can understand natural phenomena even deeper. Sound that we cannot see, light that we cannot observe the wave, we can get to know this wave more deeply, have more deeper understanding of this wave. Okay, so now we want to look at how is it that we can get the AX and D of sound wave. Okay, interference of sound wave. Interference of sound wave. So you see, this experiment, this is speaker S1, speaker S2. S1 and S2 is the source of the sound wave, right? Source of the sound wave. Boom, 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 boom. Okay. So that means the distance here and here, this will be A. And then when you turn on, what happens is you cannot see, but the wave that come out from S1 and S2, they will interfere with each other, and then they will have node, antinode, and then when you walk, if you walk from here to here, for example, this one, this is loud sound. That means this one is where we have constructive interference. That means this is where we have the antinode. Okay, antinodal line. Okay, this is where we have the antinodal line. This one is where we have the soft sound, so that means this is the nodal line. You see or not? Okay? Get the idea? So if you go from here to over here, then you will be able to hear the sound loud, soft, loud, soft, loud, soft, loud, soft. So let's say that your ear is not very accurate in detecting. So you can use microphone. You take microphone and then you slowly walk from here to here. And then the microphone is connected to cathode ray oscilloscope. Still remember cathode ray oscilloscope that you learned in Form 3. You got learn cathode ray oscilloscope, the one that got wave come out one. Okay, so what happens if the microphone detect a loud sound, the amplitude of the wave will become bigger. If the microphone detects soft sound, then the amplitude is small. You see or not? So from here, by using the microphone and the cathode ray oscilloscope, we can get a very good position of the loud and the soft sound. That means we can find out the position of nodal and antinodal line very accurately. So if we get the position of nodal and antinodal line, that means we can get X. X, right? Okay, this is soft to soft, so this is 1x. Soft to soft, that means is nodal to nodal line. The distance from soft to soft, that is x. Soft sound to soft sound, x. Loud to loud, x. Loud to loud, x. Okay? Now, if you measure perpendicular distance from the point of measuring x to the coherent wave source, the distance, then you can get d. So again, the wavelength of the sound can be calculated ax over d. Okay? Now, okay, any question? Okay, continue. Now, okay, sound done. Next, we want to look at light. Light. What is it that we can see is, if you look at this experiment, you look at this, there's a screen here, right? There's a screen here. So on this screen, we will be able to see this thing. We'll be able to see this on the screen. Okay, Anna? Okay, we'll be able to see this on the screen. okay, on the screen. Bright, dark, bright, dark, bright, dark, bright, dark. The bright part is the nodal or anti-nodal. Anti-nodal, because if it's bright, the light are bright, that means constructive interference. So that means this is anti-nodal line. The position of anti-nodal line. The dark one means there is destructive interference. So at this position we have nodal line. Okay, we have nodal line. So by measuring, because this one it will be very small, very small, very small, very small. So usually what we do is we don't measure one only lah. We measure many, many. Okay, we see what is the length here. So this is dark to dark is 1x. Dark to dark, another x. Dark to dark, dark to dark, dark to dark. See, we see have how many x? So, for example, 1, 2, 3, 4, 5, 6, 7, 8. So we have 8x. And then we see how many centimeter lah. Okay, so for example, if 2 centimeter, so we take 2 centimeter divide by 8, we get x is how much? Understand? Okay, so we get x, and then the distance from the double slit to the screen. Distance from the double slit to the screen, that is D lah. Okay, D. This double slit, this is where this is considered as the source of the light wave, of source of the coherent light wave. Okay, this double slit is the source of the coherent light wave. So the distance between the two slits, for example, this one, here to here. Here to here, the distance between the two slits, this is A lah. Okay, or this one, the small one, very small one, A. Understand? So again, we have lambda equal AX over D. We can calculate the wavelength of light. Okay, you can calculate wavelength of light. I know that right now you feel like, oh, okay, wavelength of light, okay. But I tell you, if you are the scientist that year, if you are the scientist that discovered this, I get the wavelength of light, because nobody else can find out what is the wavelength of light, because you cannot see the wave of the light, right? Relationship between variable of interference of wave. Okay, actually this is what we discussed already just now. Lambda is the wavelength, A is the distance of separation between two coherent sources, X is the distance of separation between two adjacent antinodal line or two adjacent nodal line. Okay, D is the perpendicular distance from the sources and the position where the value of X is measured. Okay, so the relationship is the lambda equal AX over D lah. Okay, so this activity is to study the relationship between lambda, AX and D. So the result is we get this lah, lambda equal AX over D. Okay, now we want to look at, okay, example. Figure 5.65 show young double slit experiment which produce interference pattern on the screen. The distance between adjacent bright fringes is 4.5 millimeter. You see, this 4.5 millimeter is distance between adjacent bright fringes. That means what? From bright to bright is 4.5 millimeter. What is the wavelength of the light used? They want you to calculate the wavelength. So A is 0.4 millimeter, D is 3 millimeter. Okay. So, D is 3 meter. So, the equation that we use is lambda equals to AX over D. Now, before you put the numbers inside this equation, there is one thing that you must make sure. Make sure what? All of the unit must be the same. You see, got mixed. This one millimeter, this one millimeter, but this one is meter. So you must make sure all of them have the same unit. For me personally, I like to change everything into meter. That is me lah. If you don't want to change everything into meter, you want to change everything into millimeter, you want to change everything into centimeter, depend on you. Okay, depend on you. Okay, so for me, I like to change everything into meter. So A is 0.4 milli 10 power negative 3 times X 4.5 milli 10 power negative 3 divided by D 3 meter. Okay, so we will be able to get, we get 6 times 10 power by negative 7 meter. So that is the wavelength of the light. Okay, wavelength of the light. So for remember, the unit is very important. You must write the unit. Must write the unit. But correct unit. Okay. Okay. Monochromatic light wave. Okay. I want to take this chance to explain to you what does it mean by monochromatic light. What is the meaning of monochromatic light? Mono means single, one only. Chrome means color. Monochrome, that means one color. Monochromatic light, that means light with one color only. What does it mean by light with one color? Or what does it mean by light that have a lot of color mixed together? Example, white light lah. White light is mixture of 7 color, right? Okay, you get white light. So if you are able to isolate the light into one color only, then you get monochromatic light. Monochromatic light basically means that the wavelength of the light is of a single wavelength. That means one type of wavelength only. Don't have different wavelength mixed inside. Another information for you is light of different color have different wavelength. Red light have longer wavelength compared to orange, shorter a bit, yellow shorter a bit, green shorter a bit, light blue shorter a bit, blue shorter a bit, and the shortest is purple or violet. Okay, so that is the arrangement of the wavelength of different color. So basically follow the rainbow color. Follow the rainbow. Red until violet. Red is the longest wavelength. Towards violet or towards the purple is shorter wavelength. Okay? So monochromatic light is light of single color. That means one wavelength only. You don't have different wavelengths mixed together. That is monochromatic light. So it says that this monochromatic light wave have a wavelength of 450 nanometer propagated through a double slit. Fringes are formed on the screen that is 4 meters away from the slit. If the distance between two consecutive bright fringes is 1.6 millimeter, what is the separation of slit? That means they want us to calculate A is how much? Okay, so again, lambda equal AX over D. Wavelength 450 nanometer, so 450 times 10 power by negative 9. Okay, make sure everything is the same unit. For me, I like to change everything into meter. A is the one that we are looking for. X is distance between two consecutive bright fringes, 1.6 millimeter. So 1.6 times 10 power by negative 3. And then divide by D is 4 meter. So A is equal to, A is 1.125 times 10 power by negative 3 meter. Okay?